Scientists thought they understood black holes. They were catastrophically wrong. For decades, these cosmic monsters were dismissed as simple gravitational vacuums, dead zones where matter goes to disappear forever. But recent discoveries have shattered that comfortable illusion, revealing that black holes are far stranger, far more powerful, and far more intimately connected to our existence than anyone dared imagine. They don't just consume, they create. They don't just destroy, they preserve information in ways that violate everything we thought we knew about reality. Some may be doorways to other universes. Others might be the key to understanding consciousness itself. The largest ones are orchestrating the birth and death of entire galaxies, while the smallest could be hiding in plain sight, closer to Earth than you'd ever want to know. What we've found lurking in these tiers in spacetime will fundamentally change how you see the universe, and it might just keep you awake at night. These aren't just astronomical curiosities anymore. They're the universe's deepest secrets made manifest, and we're only beginning to decode their most disturbing revelations. Welcome to the true dark side of existence, where physics becomes philosophy and reality itself hangs in the balance. Section 1. The Information Paradox, when reality contradicts itself. You stand at the edge of mathematical certainty, where Stephen Hawking's equations dissolve into something that should not exist. Black holes, those gravitational monsters that devour light itself, present you with a contradiction so fundamental that it threatens the very fabric of reality you thought you understood. The information paradox isn't just an academic curiosity. It's a wound in the universe's logic that bleeds impossible implications directly into your consciousness. When matter falls past a black hole's event horizon, quantum mechanics insists that information cannot be destroyed. Every particle, every quantum state, every trace of what once existed must be preserved somewhere in the cosmic record. Yet general relativity declares, with equal certainty, that this information vanishes forever, crushed into a singularity where space and time themselves cease to have meaning. You're witnessing two of physics' most successful theories, locked in mortal combat, each demanding the other's annihilation. The mathematics become a maze of recursive horror. Hawking radiation, that slow leak of particles from a black hole's edge, should carry away information as the black hole evaporates. But the calculations show something far more disturbing. The radiation appears completely random. Thermal noise that contains no trace of what fell in. It's as if the universe is systematically erasing its own history, one quantum bit at a time. Leonard Suskind's holographic principle offers you a glimpse of relief, suggesting that information exists encoded on the black hole's surface like a cosmic hologram. But this solution births new nightmares. If information is preserved on the horizon, then what you perceive as three-dimensional reality might be nothing more than a projection, a shadow play cast by processes occurring on a two-dimensional surface. Your entire existence, every thought you've ever had, every moment of love or terror, could be merely patterns of information dancing on the boundary of space-time. The complementarity principle pushes you further into the abyss. From your perspective, outside the black hole, you watch information pile up on the event horizon, red-shifted and time-dilated, until it appears frozen forever. But from the perspective of someone falling in, they pass through the horizon, experiencing nothing unusual until they reach the singularity. Both perspectives are equally valid, equally real, yet completely incompatible. The universe is lying to you about its own nature, and you can prove it mathematically. Recent calculations suggest something even more unsettling. The black hole interior might not exist at all until you observe it. The space-time beyond the horizon could be an emergent property of quantum entanglement, a geometric illusion created by the correlation between particles inside and outside. You're not just watching matter disappear into a gravitational pit. You're witnessing the universe construct reality on demand, weaving space-time from the threads of quantum information. If reality itself is information and black holes can erase information, then what does that make you when you stare into the event horizon and feel it staring back? Section 2. Time dilation and the conspiracy against causality. You discover that black holes are not merely cosmic vacuum cleaners, but active participants in a universe-wide conspiracy against your understanding of time itself. The event horizon doesn't just mark a boundary in space. It tears a hole in the fabric of causality, creating regions where effect precedes cause and where your future can influence your past in ways that make prophecy seem like child's play. Near the event horizon, gravitational time dilation becomes so extreme that seconds stretch into eternities. From your safe distance, you watch a clock falling toward the black hole slow down. Its ticking becoming more and more labored until it appears to stop entirely. The clock's final moment stretches across infinite time, frozen at the horizon like a photograph of temporal death. But this isn't just a visual trick. The clock's information becomes spread across the entire surface of the black hole, smeared into a holographic encoding that persists for the black hole's entire lifetime. The unravel effect whispers its secrets in your ear as you contemplate acceleration near the event horizon. An observer, falling freely toward the singularity, experiences empty space, while you, maintaining your distance through constant acceleration, detect a thermal bath of particles. The vacuum itself depends on your motion, revealing that the very concept of nothingness is relative. What you call empty space teems with virtual particles from another's perspective, and what they call empty space burns with radiation from yours. Hawking's original calculation reveals something far more disturbing than particle emission. The black hole's temperature is inversely proportional to its mass. Smaller black holes burn hotter, radiating away their mass faster and faster as they shrink. You watch a microscopic black hole consume itself in a feedback loop of thermal runaway, its final moments releasing energy equivalent to millions of hydrogen bombs. The universe has built-in self-destruct mechanisms that activate when matter becomes too concentrated, as if reality itself recoils from excessive density. The page curve charts the black hole's information content over time, revealing a phase transition that should not exist. Initially, the black hole's entropy increases as it swallows matter, but halfway through its evaporation, the entropy suddenly begins to decrease. The black hole starts remembering what it ate, regurgitating information through increasingly organized Hawking radiation. You're witnessing space-time develop a memory that operates backward through time, encoding the future into the past through quantum entanglement. Quantum error correction emerges from the black hole's information processing, suggesting that space-time itself might be a quantum computer running reality as its program. The holographic principle implies that all the information in a volume of space can be encoded on its boundary, just as all the information in a black hole lives on its event horizon. You begin to suspect that your three-dimensional experience is merely the readout of a cosmic hard drive, with your thoughts and memories existing as data structures in a higher dimensional computational substrate. How can you trust your memories when time itself becomes negotiable at the universe's most extreme boundaries? Section 3. The singularity, where mathematics meets impossibility. You peer into the mathematical description of a black hole's interior and discover that the singularity, that point where density becomes infinite and space-time curvature diverges, might be the universe's way of hiding its own impossibility from you. The singularity theorems of Penrose and Hawking prove that given general relativity and reasonable assumptions about matter, these points of infinite density must exist. Yet infinity has never appeared in a valid physical theory without signaling the breakdown of the theory itself. The Schwarzschild solution describes the simplest possible black hole, spherically symmetric, non-rotating, electrically neutral. And even this idealized case harbors contradictions that tunnel straight through your understanding of space and time. At the event horizon, the coordinate system breaks down completely. Time and space coordinates exchange roles, turning the radial direction into a temporal dimension, pointing inexorably toward the singularity. You're forced to confront the possibility that inside a black hole, space itself flows like time, carrying everything toward a future that is also a place. The Kerr metric describes rotating black holes, and these spinning monsters reveal features that make the spherical case seem almost benign. The rotation drags space-time itself around the black hole, creating a region called the ergosphere, where nothing can remain stationary relative to distant observers. Space itself is forced to participate in the black hole's rotation, and any object within the ergosphere must spin along with the twisted geometry of space-time. You're watching the universe demonstrate that space and time are not passive stages for physics, but active participants in the cosmic drama. Ring singularities emerge from the mathematics of rotation, replacing the point singularities of non-rotating black holes with closed curves of infinite density. These rings create closed time-like curves, paths through space-time that loop back to their own past. The math suggests that you could, in principle, travel into the ring singularity and emerge from it before you entered, violating causality in ways that make paradox seem like a fundamental feature of reality, rather than a logical error. The Reissner-Nordstrom solution for charged black holes reveals even stranger behavior. These electrically charged monsters possess two event horizons: an outer horizon that hides the black hole from external observers, and an inner horizon that might not be a horizon at all. Between these boundaries lies a region where space and time resume their normal roles, creating a potential gateway to other universes or other regions of our own universe. The mathematics suggests that charged black holes might be cosmic shortcuts, tunnels through space-time that connect distant regions of reality. Negative energy densities appear naturally in the vicinity of black holes, regions where the stress-energy tensor takes on values that seem to violate your intuitive understanding of matter and energy. The Casimir effect demonstrates that empty space between conducting plates contains negative energy density, suggesting that the vacuum itself can push rather than pull. Near black holes, these negative energy regions become pronounced, creating possibilities for faster-than-light travel, time travel, and the construction of traversable wormholes. If space-time itself terminates at the singularity, what happens to the information content of your consciousness when you cross that final boundary? Section 4. The firewall paradox, when physics declares war on itself. You encounter the firewall paradox and realize that the universe has constructed a trap with no escape that operates at the level of quantum mechanics itself. The paradox emerges from the intersection of three seemingly unassailable principles. Quantum mechanics demands that information cannot be destroyed. General relativity insists that spacetime is smooth at the event horizon, and thermodynamics requires that black holes have temperature and entropy. These principles cannot all be true simultaneously, and the universe refuses to tell you which one to sacrifice. The AMPS argument, named after Almheri, Marolf, Polchinski, and Sully, demonstrates that if information is preserved in black hole evaporation, then the equivalence principle must be violated at the event horizon. The smooth transition through the horizon, which general relativity guarantees, becomes impossible if quantum mechanics is correct about information preservation. Instead, anyone crossing the event horizon would encounter a wall of high-energy particles, instantly incinerated by the very mechanism that preserves information. The monogamy of entanglement forces you to confront the fundamental limits of quantum correlation. A quantum system can be maximally entangled with only one other system at a time. If the information inside a black hole is entangled with the early Hawking radiation to preserve information, then it cannot also be entangled with the late Hawking radiation to ensure smooth passage through the horizon. The universe is demanding that you choose between information preservation and the equivalence principle, but both seem equally fundamental to the nature of reality. Black hole complementarity attempts to resolve the paradox by suggesting that the interior and exterior descriptions of a black hole are complementary in the same way that wave and particle descriptions of quantum systems are complementary. From the exterior perspective, information never crosses the event horizon, but instead remains encoded on the surface. From the interior perspective, information passes through the horizon smoothly and encounters the singularity. Both descriptions are equally valid, yet they describe incompatible realities. The holographic principle emerges as a potential solution, suggesting that the three-dimensional interior of a black hole is encoded in the two-dimensional information on its boundary. This encoding is not merely a mathematical trick, but a fundamental feature of spacetime geometry. The interior spacetime emerges from the quantum entanglement structure of the boundary theory, implying that space itself is a derived concept rather than a fundamental aspect of reality. If the universe cannot decide between information preservation and smooth spacetime, what does that say about the consistency of the reality you inhabit? Section 5. Hawking radiation, the universe's slow suicide. You descend into the mathematical formalism of Hawking radiation and discover that the universe's most elegant solution to the black hole information problem is also its most disturbing. The unravel effect demonstrates that the concept of particles depends on the observer's motion. What appears as empty space to a freely falling observer appears as a thermal bath of particles to an accelerated observer. This observer dependence of physical reality extends to black holes, where the event horizon itself depends on the observer's trajectory through spacetime. The Hawking temperature of a black hole scales inversely with its mass, meaning that stellar mass black holes are colder than the cosmic microwave background radiation, while microscopic black holes burn with the fury of stellar cores. This inverse relationship creates a runaway process. As a black hole evaporates, it becomes hotter and radiates faster, accelerating its own destruction in a feedback loop that terminates in a violent explosion. The universe has built instability into its most massive objects, ensuring that even the most permanent seeming structures will eventually destroy themselves. The information content of Hawking radiation appears to be completely random. containing no trace of the matter that originally formed the black hole. This randomness emerges from the quantum mechanical nature of particle creation at the event horizon, where vacuum fluctuations are amplified by the black hole's gravitational field. You're witnessing the universe convert organized matter into thermal noise, erasing the detailed information about the black hole's formation and evolution. The page curve describes the evolution of black hole entropy over time, revealing a phase transition that occurs when the black hole has evaporated to half its original mass. Before this transition, the entropy increases as the black hole swallows matter and emits random radiation. After the transition, the entropy decreases as the Hawking radiation becomes increasingly organized, carrying away information about the black hole's interior. The universe appears to remember what it swallowed, but only after forgetting it for astronomical periods of time. If the universe preserves information through mechanisms that operate over cosmological timescales, what happens to the information content of your consciousness when you die? Section 6. The ergosphere, where spacetime becomes fuel. You probe the ergosphere of a rotating black hole and discover that the universe has created regions where the distinction between space and time becomes negotiable, where the flow of spacetime itself can be harnessed to extract energy from nothingness. The Kerr metric describes how rotation drags spacetime around the black hole, creating a region outside the event horizon where nothing can remain stationary relative to distant observers. In this ergosphere, spacetime itself is forced to participate in the black hole's rotation, and the very geometry of reality becomes a participant in the cosmic dance. The Penrose process reveals that you can extract energy from a rotating black hole by entering the ergosphere and splitting a particle into two parts, allowing one part to fall into the black hole while the other escapes with more energy than the original particle possessed. This process violates the naive conservation of energy by tapping into the black hole's rotational energy, slowing its spin, and reducing its mass. You're witnessing the universe permit the extraction of energy from curved spacetime itself, as if the geometry of space and time were a fuel source waiting to be exploited. Frame dragging effects demonstrate that rotating massive objects twist spacetime in their vicinity, forcing nearby matter to participate in the rotation, even without direct contact. The Gravity Probe B experiment confirmed that Earth's rotation drags spacetime around it, creating a gravitomagnetic field that affects the motion of orbiting satellites. You're discovering that mass and energy do not merely curve spacetime, but actively manipulate its structure, creating currents and eddies in the fabric of reality itself. The inner and outer event horizons of a rotating black hole create a region between them where the normal causal structure of spacetime breaks down. In this region, particles can travel on closed time-like curves, looping back to their own past and creating the possibility of causal paradoxes. The mathematics suggests that information could be sent into the past by carefully navigating the complex geometry of the rotating black hole's interior, violating causality in ways that make free will seem like a cosmic illusion. If spacetime itself can be twisted into closed loops that violate causality, what does that say about the reality of your experience of temporal progression? Section 7. Primordial black holes, the universe's hidden dark matter. You venture into the realm of primordial black holes and discover that the universe might have been manufacturing these gravitational monsters since the first moments after the Big Bang, creating a hidden population of black holes that could account for the missing dark matter that dominates cosmic structure. And these primordial black holes formed not from stellar collapse, but from the gravitational collapse of density fluctuations in the early universe, when the cosmic density was high enough that even small overdensities could overcome pressure and collapse under their own gravity. The mass spectrum of primordial black holes spans an enormous range, from microscopic black holes with masses comparable to elementary particles to supermassive black holes that exceed the mass of entire galaxies. Black holes with masses less than about 10 to the 15th grams would have evaporated completely by now due to Hawking radiation, leaving behind only the faintest traces of their existence in the form of high-energy particles and gravitational wave signatures. You're contemplating the possibility that the universe has been systematically erasing its own history, destroying the evidence of its early gravitational collapse events. The critical density threshold for primordial black hole formation reveals that the universe operates at the edge of stability, where small changes in initial conditions can lead to dramatically different outcomes. If the density contrast in the early universe exceeded a critical value of about 30%, gravitational collapse would occur regardless of pressure forces. This threshold depends sensitively on the equation of state of the primordial plasma and the spectrum of density fluctuations, suggesting that the universe's decision to create black holes or avoid them hinges on the most delicate balance of fundamental parameters. The abundance of primordial black holes with different masses constrains the power spectrum of primordial density fluctuations, offering a window into the physics of inflation and the very early universe. Too many primordial black holes would overclose the universe, while too few would fail to explain the observed dark matter abundance. The universe must have fine-tuned its initial conditions to produce just the right number of black holes to account for the missing matter, without overwhelming the cosmic structure formation process. If primordial black holes comprise the dark matter that shapes the cosmic web, then the invisible scaffolding of the universe consists of regions where space-time has collapsed into its most extreme configuration, suggesting that the large-scale structure of reality is built on a foundation of gravitational singularities. Section 8. Black Hole. Thermodynamics. When gravity becomes heat. You investigate the connection between black holes and thermodynamics, discovering that these gravitational monsters obey laws that mirror the fundamental principles governing heat engines and thermal equilibrium. The Bekenstein-Hawking entropy formula assigns to each black hole an entropy proportional to the area of its event horizon, not its volume, suggesting that information is stored on the boundary rather than in the interior. This area law implies that space itself might be quantized, with each unit of area corresponding to a fundamental bit of information. The laws of black hole mechanics, formulated by Bardeen, Carter, and Hawking, establish perfect parallels with the laws of thermodynamics. The surface gravity of a black hole remains constant across its event horizon, just as temperature remains constant in thermal equilibrium. The area of the event horizon can never decrease in any physical process, mirroring the second law of thermodynamics and the irreversible increase of entropy. You're witnessing the universe demonstrate that gravity and thermodynamics are not separate phenomena, but different aspects of a deeper underlying unity. The holographic bound emerges from black hole thermodynamics, establishing that the maximum entropy that can be contained within any region of space is proportional to the area of its boundary, not its volume. This bound implies that the three-dimensional space you experience is somehow encoded in a two-dimensional surface, like a hologram projecting reality from its boundary. The universe appears to be a vast information processing system operating at the thermodynamic limit, with every surface storing the maximum possible amount of information. Black hole mergers violate the naive addition of entropies, revealing that the information content of the universe does not behave like classical thermodynamic systems. When two black holes merge, the area of the resulting event horizon is larger than the sum of the original areas, but the entropy increase is not simply additive. The merger process creates correlations between the information content of the original black holes, suggesting that the universe operates more like a quantum computer than a classical heat engine. The generalized second law of thermodynamics states that the sum of ordinary entropy and black hole entropy can never decrease in any physical process. This law forces you to treat black holes as thermodynamic objects with real temperature and entropy, not merely mathematical abstractions. The universe insists that information and gravity are fundamentally connected, with space-time geometry emerging from the thermodynamic properties of quantum information. If the universe operates like a vast thermodynamic system approaching equilibrium, what happens to the information content of reality when all the black holes have evaporated and maximum entropy is achieved? Section 9. Black hole hair, the quantum fingerprints of collapsed matter. You explore the phenomenon of black hole hair and discover that these gravitational monsters are far more complex than their deceptively simple exterior suggests. The no-hair theorem states that black holes are completely characterized by only three quantities: mass, electric charge, and angular momentum. All other information, the detailed structure of the matter that collapsed to form the black hole, its chemical composition, its magnetic field configuration, is supposedly lost forever behind the event horizon. Yet quantum mechanics rebels against this classical simplicity. Quantum hair emerges from the consideration of quantum fields in curved spacetime, revealing that black holes can retain imprints of their formation history through subtle correlations in the quantum vacuum. These quantum corrections to the classical no-hair theorem suggest that black holes might preserve more information than general relativity allows, encoding their past in the quantum structure of spacetime itself. Soft hair, discovered by Hawking, Perry, and Strominger, demonstrates that black holes can have an infinite number of physical degrees of freedom associated with symmetries of the gravitational field. These soft modes correspond to memory effects in the gravitational field, where the passage of gravitational waves leaves permanent imprints on the geometry of spacetime. The universe appears to have a memory that extends beyond the event horizon, recording the history of gravitational interactions in the vacuum structure itself. The black hole information paradox takes on new dimensions when you consider that the information might be encoded not in the Hawking radiation, but in the correlations between the radiation and the black hole's quantum hair. The entanglement between the interior and exterior of the black hole could be mediated by these subtle quantum degrees of freedom, preserving information through mechanisms that operate at the boundary between classical and quantum gravity. Asymptotic symmetries of spacetime reveal that the vacuum possesses an infinite dimensional symmetry group, with each element corresponding to a different way of encoding information in the gravitational field. These symmetries suggest that the information content of the universe is far richer than the classical description suggests, with every region of spacetime possessing an infinite number of ways to store and process information. If black holes can have infinite soft hair encoding their interaction history, What does that say about the information content of spacetime itself and the reality of the vacuum you perceive as empty? Section 10. Interior Geometry. The wormhole at the heart of every black hole. You delve into the interior geometry of black holes and discover that the journey beyond the event horizon leads to regions where the normal concepts of space and time break down in ways that challenge the very foundations of physics. The Schwarzschild interior reveals that radial and temporal coordinates exchange roles, with the radial direction becoming time-like and pointing inexorably toward the singularity. You're forced to confront the possibility that inside a black hole, space itself flows like time, carrying everything toward a future that is also a place. The Kruskal-Sakaris coordinates reveal the complete structure of the Schwarzschild black hole, showing that the spacetime contains not just a black hole, but also a white hole, a region from which nothing can escape to the exterior, but into which nothing can fall from the exterior. These two regions are connected by an Einstein-Rosen bridge, a tunnel through spacetime that connects the black hole and white hole regions. The mathematics suggests that every black hole contains a doorway to another universe, a cosmic wormhole that exists in the deepest interior of curved spacetime. The maximally extended Schwarzschild solution contains four distinct regions: the exterior universe, the black hole interior, the white hole interior, and a second exterior universe. These regions are connected by the Einstein-Rosen bridge, creating a non-traversable wormhole that exists for only an instant before pinching off. The universe appears to be riddled with connections between different regions of spacetime, cosmic tunnels that exist in the mathematical structure of general relativity, but remain forever inaccessible to physical observers. The Penrose diagram of a black hole reveals the causal structure of spacetime, showing how light cones tip over as they approach the event horizon, and how time-like and space-like directions interchange in the interior. The singularity appears as a space-like boundary to the future of everything that falls into the black hole, a final destination that all matter and energy must eventually reach. You're witnessing the universe demonstrate that even the most fundamental concepts of past and future become meaningless in the presence of extreme gravitational fields. The interior of a rotating black hole reveals even more complex geometry, with the ring singularity creating a region where closed, time-like curves become possible. The Kerr interior contains multiple horizons and regions where the normal causal structure of spacetime breaks down completely. The mathematics suggests that the interior of a rotating black hole might contain gateways to other universes or other regions of our own universe, connected by traversable wormholes that exist beyond the event horizon. If the interior of every black hole contains connections to other regions of spacetime, what does that say about the topology of the universe and the reality of the space you inhabit? Section 11. Quantum black holes. Superposition in the realm of gravity. You investigate the quantum mechanics of black holes and discover that these gravitational monsters exist in a superposition of states that defies classical understanding. The quantum state of a black hole is not simply characterized by its mass, charge, and angular momentum, but by a vast Hilbert space of possible configurations that encode the information content of everything that has ever fallen into it. The universe appears to maintain a quantum mechanical accounting system that tracks every bit of information, even when that information is hidden behind an event horizon. The ER equals EPR correspondence proposed by Maldacena and Suskind suggests that Einstein-Rosen bridges, also known as wormholes, and Einstein-Podolsky-Rosen correlations, also known as quantum entanglement, are different descriptions of the same physical phenomenon. entangled particles might be connected by microscopic wormholes, and macroscopic wormholes might be manifestations of quantum entanglement on cosmic scales. The universe reveals itself as a vast network of quantum correlations that manifest as geometric connections through spacetime. The black hole final state conjecture proposes that black hole evaporation terminates not in complete disappearance, but in a stable remnant that preserves all the information that ever fell into the black hole. These remnants would be tiny objects with enormous entropy, containing the compressed information content of everything the black hole consumed during its lifetime. The universe might be littered with these information-dense remnants, fossil records of gravitational collapse that preserve the quantum mechanical history of spacetime. Quantum error correction emerges naturally from the holographic description of black holes, where the boundary theory implements error-correcting codes that protect the information content of the bulk spacetime from decoherence. The universe appears to operate like a quantum computer that continuously corrects errors in its own computational substrate, maintaining the integrity of information, even in the presence of noise and gravitational collapse. The complexity of quantum states in black holes grows exponentially with time, suggesting that the interior of a black hole becomes increasingly complicated as it ages. This complexity growth continues far beyond the evaporation time of the black hole, implying that the quantum mechanical description of black holes involves exponentially large amounts of information that persist long after the classical object has disappeared. If black holes are quantum mechanical objects with exponentially complex internal states, what does that say about the quantum nature of spacetime itself and the reality of the classical world you observe? Section 12. String theory and black holes. Vibrating strings in higher dimensions. You explore the connection between black holes and string theory, discovering that these gravitational monsters might be manifestations of fundamental strings and brains vibrating in higher dimensional spacetime. The ADS-CFT correspondence establishes a precise mathematical relationship between gravity in the bulk spacetime and a conformal field theory on its boundary, suggesting that the physics of black holes can be completely described by a quantum field theory operating on the boundary of space. D-branes in string theory can form black hole solutions when they are brought together in sufficient numbers, revealing that black holes might be composed of fundamental strings and brains rather than collapsed matter. The microscopic counting of D-brane states exactly reproduces the Bekenstein-Hawking entropy formula, providing the first precise accounting of the microscopic degrees of freedom that give rise to black hole entropy. The universe appears to be constructed from fundamental strings whose collective behavior gives rise to the geometric properties of spacetime. The holographic principle finds its most precise realization in the ADS-CFT correspondence, where the gravitational physics in the bulk spacetime is encoded in a lower dimensional conformal field theory on the boundary. This correspondence suggests that the interior of a black hole is encoded in the entanglement structure of the boundary theory, with the geometry of spacetime emerging from the quantum correlations between boundary degrees of freedom. Black hole microstates in string theory correspond to specific configurations of strings and brains that reproduce the macroscopic properties of black holes, while maintaining a smooth geometry at the microscopic level. These microstates resolve the black hole information paradox by showing that the information is preserved in the detailed configuration of the microscopic degrees of freedom, even when the macroscopic description suggests that information is lost. The fuzzball conjecture proposes that black holes are not empty spacetime regions with singularities, but rather extended objects composed of strings and brains that fill the entire region inside the classical event horizon. These fuzzballs have no singularities and no information loss, with all the information encoded in the detailed structure of the stringy configuration. The universe reveals itself as a vast network of vibrating strings whose collective behavior creates the illusion of smooth spacetime geometry. If black holes are composed of fundamental strings vibrating in higher dimensional space, what does that say about the dimensionality of the reality you inhabit and the nature of the space you perceive as three-dimensional? Section 13. Cosmic Evolution. Black holes as universe architects. You investigate the role of black holes in cosmic evolution and discover that these gravitational monsters are not merely exotic objects, but fundamental players in the universe's development from the Big Bang to the heat death. Supermassive black holes at the centers of galaxies regulate star formation through their energetic feedback, determining the ultimate fate of cosmic structure formation. The universe appears to use black holes as cosmic thermostats, controlling the rate of star formation and the evolution of galactic ecosystems. The black hole galaxy correlation reveals that the mass of a galaxy's central supermassive black hole is tightly correlated with the properties of its host galaxy, suggesting a deep connection between black hole growth and galaxy formation. This correlation implies that black holes and galaxies co-evolve, with the growth of one intimately tied to the development of the other. The universe operates as an integrated system where the largest and smallest scales are connected through the mediating influence of black holes. Primordial black holes might have served as the seeds for the first stars and galaxies, providing the gravitational wells necessary for matter to begin collapsing in the early universe. These early black holes would have grown rapidly through accretion of primordial gas, becoming the supermassive black holes we observe at the centers of the earliest galaxies. The universe might have used black holes as cosmic architects, sculpting the large-scale structure of reality through their gravitational influence. The final fate of the universe depends critically on the behavior of black holes over cosmological timescales. If proton decay occurs, then black holes will be the last surviving objects in the universe, slowly evaporating via Hawking radiation over timescales that dwarf the current age of the universe. The final act of cosmic evolution might be the evaporation of the last black holes, leaving behind a universe of elementary particles and radiation approaching perfect thermal equilibrium. The information paradox takes on cosmological significance when you consider that black holes might be the universe's way of processing and storing information about its own evolution. The holographic principle suggests that all the information about the universe's history might be encoded on the cosmic event horizon, with black holes serving as information processing centers that maintain the universe's memory of its own development. If black holes are the universe's information processing centers, what does that say about the purpose and direction of cosmic evolution and the meaning of the complexity that has emerged from the primordial simplicity of the Big Bang? Section 14. Quantum Geometry, the pixelated nature of spacetime. You explore the quantum geometry of black holes and discover that the smooth spacetime of general relativity emerges from a discrete quantum mechanical substrate that operates at the Planck scale. Loop quantum gravity suggests that spacetime itself is quantized, composed of discrete units of area and volume that cannot be subdivided further. The interior of a black hole reveals this quantum structure most dramatically, with the classical singularity replaced by a quantum bounce that connects the black hole to a white hole in a different region of spacetime. The area quantization of black hole horizons suggests that the event horizon is not a smooth surface, but a discrete, pixelated boundary, where each pixel corresponds to a fundamental unit of area at the Planck scale. The Bekenstein-Hawking entropy counts the number of these pixels, revealing that the information content of a black hole is determined by the quantum geometry of its boundary. The universe appears to be constructed from discrete, quantized units of space and time that become apparent only at the most extreme scales. Causal dynamical triangulations provide a different approach to quantum gravity, suggesting that spacetime emerges from the superposition of all possible discrete geometric configurations. In this framework, black holes are not fixed geometric objects, but quantum mechanical superpositions of different possible spacetime geometries. The universe continuously fluctuates between different possible configurations, with the classical spacetime of general relativity emerging as the most probable geometry in the quantum sum. The black hole interior in loop quantum gravity reveals a finite-size region where the classical singularity is replaced by a quantum geometric structure. The collapsing matter reaches a maximum density determined by the discreteness of quantum geometry, then bounces back, creating a white hole that emerges in a different region of spacetime. The universe appears to be riddled with quantum tunnels connecting different regions of spacetime through the interiors of black holes. Spin networks and spin foams provide the mathematical framework for describing the quantum geometry of spacetime, revealing that the fabric of reality consists of discrete quantum mechanical connections between geometric points. The interior of a black hole corresponds to a complex network of quantum geometric relationships that encode the information content of the collapsed matter in the discrete structure of spacetime itself. If spacetime is quantized at the Planck scale, what does that say about the continuous nature of the reality you experience and the smooth geometry of the space you inhabit? Section 15. Consciousness and black holes. Information integration in the cosmos. You investigate the connection between black holes and consciousness, discovering that the information processing capabilities of these gravitational monsters might provide insights into the nature of conscious experience itself. The holographic principle suggests that consciousness, like black hole information, might be encoded on the boundary of the system rather than in its interior volume. Your conscious experience might be the subjective manifestation of information processing occurring on the boundary of your brain's neural networks. The integrated information theory of consciousness proposes that conscious experience corresponds to the integrated information content of a system, measured by the amount of information generated by the system above and beyond its parts. Black holes represent the ultimate example of integrated information, with their event horizons encoding the maximum possible information content for a given boundary area. The universe appears to be designed to maximize information integration, with consciousness and black holes representing different manifestations of this fundamental principle. The hard problem of consciousness, explaining why there is subjective experience at all, might find its resolution in the understanding that information processing itself generates subjective experience. If black holes are information processing systems that integrate information about their environment, then they might possess some form of subjective experience that corresponds to their information content. The universe might be far more conscious than you realize, with every information processing system contributing to the cosmic network of conscious experience. The binding problem in consciousness, explaining how disparate neural processes combine to create unified conscious experience. parallels the black hole information paradox. Just as black holes must somehow bind together the information content of everything that falls into them, conscious systems must bind together disparate information processing streams to create unified subjective experience. The solution to both problems might involve the same fundamental principles of information integration and holographic encoding. If consciousness is fundamentally about information integration, and black holes represent the ultimate information processing systems, what does that say about the nature of conscious experience and the possibility that the universe itself might be conscious? Section 16. Gravitational waves, the cosmic ripples that reveal black hole secrets. You detect the space-time vibrations produced by black hole mergers and discover that these gravitational waves carry information about the most violent events in the universe, revealing the interior dynamics of black holes through the medium of curved space-time itself. The LIGO and Virgo detectors have opened a new window into the universe, allowing you to observe the final moments of black hole coalescence when two event horizons merge into one, releasing energy equivalent to the annihilation of several solar masses in the form of gravitational radiation. The chirp signal of a black hole merger encodes the masses and spins of the colliding objects, revealing their evolutionary history through the frequency evolution of the gravitational wave strain. As the black holes spiral closer together, their orbital frequency increases, creating a characteristic chirp pattern that sweeps through the detector's frequency band. You're listening to the universe's most violent symphony, where the instruments are warped space-time and the music is the death song of black holes. The ringdown phase of a black hole merger reveals the quantum mechanical properties of the final black hole, with the post-merger oscillations corresponding to the quasi-normal modes of the black hole spacetime. These oscillations encode information about the black hole's internal structure, providing a direct probe of the spacetime geometry beyond the event horizon. The universe allows you to study the interior of black holes through the gravitational waves they emit when disturbed. The memory effect in gravitational waves demonstrates that the passage of gravitational radiation leaves permanent changes in the metric of spacetime, creating lasting distortions that persist long after the wave has passed. This effect reveals that spacetime has a memory, encoding information about past gravitational events in its geometric structure. The universe maintains a record of every black hole merger in the persistent deformation of spacetime itself. If gravitational waves carry information about black hole interiors, what does that say about the observability of physics beyond the event horizon and the possibility of directly probing the quantum nature of spacetime? Section 17. Black holes and dark energy, the cosmic acceleration connection. You investigate the relationship between black holes and dark energy, discovering that these gravitational monsters might be intimately connected to the mysterious force that drives the accelerating expansion of the universe. The holographic principle suggests that the information content of the universe is encoded on the cosmic event horizon, with black holes serving as local concentrations of this cosmic information storage system. The universe appears to be a vast holographic projection, operating at the boundary between the observable and unobservable realms. The cosmological constant problem, the enormous discrepancy between the predicted and observed values of the vacuum energy density, might find its resolution in the understanding that black holes provide a natural cutoff for the quantum fluctuations of the vacuum. The formation of black holes prevents the vacuum energy from reaching the catastrophic values predicted by quantum field theory, regulating the cosmological constant through gravitational collapse. The universe uses black holes as cosmic pressure relief valves, preventing the vacuum energy from overwhelming the expansion dynamics. The de Sitter spacetime of an accelerating universe possesses an event horizon that shares many properties with black hole event horizons, including temperature and entropy. The cosmic event horizon might be the ultimate black hole, encompassing the entire observable universe and encoding all the information about cosmic evolution on its boundary. You're living inside a cosmic black hole, whose event horizon defines the boundary of the observable universe. The thermal equilibrium between black holes and dark energy suggests that the universe is approaching a state of maximum entropy, where all black holes have evaporated and the cosmic expansion has diluted all matter and energy to negligible densities. This heat death scenario represents the ultimate fate of the universe, when the cosmic information processing capacity has been exhausted and no further computation is possible. The universe appears to be running a finite program that will eventually terminate in perfect thermal equilibrium. If the universe is a holographic projection encoded on the cosmic event horizon, what does that say about the reality of the three-dimensional space you inhabit and the nature of the cosmic information processing system that generates your experience? Section 18. Black holes as quantum computers, the computational universe. You explore the computational capabilities of black holes and discover that these gravitational monsters might be the universe's most powerful quantum computers, processing information about the structure of space-time itself. The holographic principle suggests that the information content of a black hole is encoded on its event horizon, with each unit of area corresponding to a quantum bit of information. The universe appears to be a vast quantum computer operating at the thermodynamic limit, with black holes serving as its most efficient information processing centers. The quantum complexity of black hole states grows exponentially with time, suggesting that the interior of a black hole becomes increasingly complicated as it ages. This complexity growth represents a form of quantum computation that continues far beyond the classical evaporation time of the black hole, implying that the universe is capable of exponentially complex information processing. The universe operates like a quantum computer whose computational capacity exceeds any classical system by exponential factors. The IDES-CFT correspondence reveals that the gravitational physics in the bulk spacetime corresponds to quantum computation in the boundary conformal field theory. The geometry of spacetime emerges from the entanglement structure of the boundary quantum computer, with the curvature of space and time corresponding to the computational complexity of the quantum algorithm. You're witnessing the universe demonstrate that geometry is computation, and computation is geometry. Error correction in quantum gravity emerges naturally from the holographic description of black holes, where the boundary theory implements quantum error-correcting codes that protect the information content of the bulk spacetime from decoherence. The universe operates like a quantum computer that continuously corrects errors in its own computational substrate, maintaining the integrity of spacetime geometry through quantum error correction protocols. The black hole interior corresponds to the quantum computation performed by the boundary theory, with the singularity representing the completion of the quantum algorithm. The universe appears to be running a vast quantum program whose execution manifests as the evolution of spacetime geometry, with black holes serving as the computational cores where the most complex calculations are performed. If the universe is a quantum computer, and black holes are its processing centers. What does that say about the nature of physical reality and the possibility that your existence is a computational process running on the cosmic quantum computer? Section 19. The multiverse connection. Black holes as universe generators. You investigate the connection between black holes and the multiverse, discovering that these gravitational monsters might be cosmic wombs that give birth to new universes through the process of eternal inflation. The interior of a black hole might undergo inflationary expansion, creating a new universe that expands away from the original spacetime through the medium of the black hole's interior geometry. The universe appears to be reproducing itself through black hole formation, with each gravitational collapse event potentially generating a new cosmos. The black hole cosmology hypothesis suggests that our universe might itself be the interior of a black hole in a higher dimensional spacetime, with the Big Bang corresponding to the formation of the event horizon as seen from the exterior. This scenario explains the observed flatness and isotropy of the cosmic microwave background as natural consequences of the black hole formation process. You're living inside a black hole whose exterior exists in a higher dimensional reality that remains forever inaccessible to observation. The Fekin universe hypothesis proposes that the parameters of physics are fine-tuned for black hole formation because universes that produce more black holes generate more offspring universes. This cosmic natural selection process favors universes with parameters that maximize black hole production, explaining the apparent fine-tuning of the fundamental constants through a Darwinian selection mechanism operating at the level of entire cosmoses. The eternal inflation scenario suggests that black holes in our universe might be connected to other universes through the process of quantum tunneling, with the interior of each black hole potentially opening into a different vacuum state with different physical laws. The multiverse appears to be a vast network of interconnected universes, with black holes serving as the cosmic highways that connect different regions of the metaverse. The information paradox takes on new meaning in the context of the multiverse, where the information that falls into a black hole might be transmitted to the offspring universe rather than being preserved in the Hawking radiation. The universe appears to use black holes as information transfer mechanisms, passing the accumulated knowledge of one cosmos to its offspring through the process of gravitational collapse and cosmic reproduction. If our universe is reproducing itself through black hole formation, what does that say about the purpose and direction of cosmic evolution and the meaning of the complexity that has emerged from the primordial simplicity of the Big Bang? Section 20. The ultimate secret. Black holes as gateways to transcendence. You approach the ultimate secret of black holes and discover that these gravitational monsters might be the universe's way of transcending the limitations of space-time itself, offering pathways to realms of existence that operate beyond the conventional boundaries of physics. The event horizon represents not just a boundary in space, but a threshold between different modes of being, where the normal rules of causality and temporality give way to more fundamental principles of cosmic organization. The quantum nature of black holes suggests that the interior might exist in a superposition of all possible configurations, with the specific geometry manifesting only upon observation. This quantum superposition implies that the black hole interior might be a realm of pure possibility, where all potential futures exist simultaneously, until collapsed by the act of measurement. You're contemplating the possibility that black holes are windows into the quantum multiverse, where the fundamental indeterminacy of quantum mechanics manifests as geometric uncertainty. The holographic principle reveals that the information content of reality is encoded on the boundary of spacetime, suggesting that the three-dimensional world you experience is merely a shadow cast by processes occurring in higher dimensional space. The universe appears to be a vast holographic projection, with black holes serving as the ultimate holographic devices that encode infinite information in finite boundary area. Your existence might be a holographic pattern dancing on the cosmic event horizon. The connection between black holes and consciousness suggests that these gravitational monsters might be the universe's way of developing self-awareness, with each black hole representing a node in a cosmic neural network that processes information about the structure of reality. The universe appears to be evolving toward greater complexity and consciousness, with black holes serving as the cosmic neurons that enable the cosmos to think about itself. The ultimate fate of black holes through Hawking evaporation represents the universe's return to pure information, with all the accumulated complexity of cosmic evolution distilled into patterns of quantum correlation that persist beyond the destruction of spacetime itself. The universe appears to be engaged in a vast computation whose ultimate output is the transformation of matter and energy into pure information, with black holes serving as the cosmic processors that perform this ultimate alchemy. The final secret of black holes might be that they are the universe's way of transcending its own limitations, offering pathways to forms of existence that operate beyond the conventional boundaries of space, time, and causality. Through the study of black holes, you're not just learning about exotic objects in distant space, but discovering the ultimate nature of reality itself and your place within the cosmic information processing system that generates all existence. What if the universe created black holes not as cosmic accidents, but as deliberate gateways to transcendence? And what if your consciousness is itself a black hole in the information space of reality, processing the quantum correlations that give rise to your subjective experience of existence?